The other big operation that we need to cover with matrices is matrix multiplication, and it's a little bit different to the way matrix addition really works. To demonstrate this, I've taken the resultant matrix from the last set of videos. So this was our total matrix for the athletics and sports carnivals for each house. So I've called that T to represent total. And matrix multiplication can be thought of in terms of, in this particular context, as a way of scaling the different results. So let's say this was the final matrix and we wanted to work out some points to add towards the total of the house competition for the year. And let's say we wanted to offer first place be 3 points, second be 2, and third be worth 1 point to the house total at the end of the year. Well, what we could do is we could represent this scaling as a column matrix. So let's reconsider this as a matrix 3, 2, 1. And just like multiplying regular numbers, we can scale things up or down by, say, doubling them or halving them or whatever. We can scale this matrix by multiplying it against a scale matrix, okay, a column matrix here. So what I'm going to do is I'm going to do this matrix T, which is quite a big, complicated one. And I haven't made it big enough, so I'll redo those brackets. I'm going to do this matrix by some scale factor 3, 2, 1. Okay, 3 points for first, 2 points for second, 1 point for third. And the resultant matrix should give us the total number of points that each house is going to get. Now, if you remember, this first column represented the number of first places, second column represented the number of second places, and the third column represented the number of third places. So each of those columns needs to get multiplied by the appropriate number. So the 3 needs to multiply by the first column, the 2 needs to multiply by the second column, the 1 needs to multiply by the third column, and then each house has to have its total points by each of those scales added together to give us our final result. So this is actually going to be quite a complicated process. Let's think about these one at a time. Okay, so Draco was the first row. To work out Draco's total, I'm going to do the 13 times the 3, because each of those 13 first places is worth 3 points. Then I'm going to do 16 times 2. Then I'm going to do 5 times 1. Okay. Then I'm going to do the same process for Hydra and for Orion and Phoenix. So the next one, 14 times 3. 6 times 2, 11 times 1, and so on. Let's keep going. Okay, so we can see here there's going to be a lot of calculation that needs to go into working out the results for this matrix. So to work out the first cell, I'm going to need to do all of these sums, 13 times 3 and 16 plus times 2 and 5 times 1, and then add them all together. So let's just jump ahead and have a look at what those results are. Once we do all of those big messy calculations, this here is the matrix that we're left with. Let's just interpret exactly what this means. This means that overall, Draco House is going to have 76 points added to the total. Hydra is going to be 65, Orion 68, and Phoenix is 91. So overall, actually, we can determine that based on this scaling, Phoenix becomes the winner. Now, this is how we define matrix multiplication. We do each element in each row by each element in each column in the second matrix. Okay, this is a bit difficult to get your head around because of the way things have to line up, elements matching with elements and then adding together. But once this process has been defined, it has a lot of really nice applications. Let's have a look at another example just to get our heads around how matrix multiplication is going to work. I'm just going to pick two random matrices that we're allowed to multiply together. That one's not very creative. And I'm going to multiply by, let's go a 3 by 2 matrix. And just to break the pattern, I might just mix this one up a little bit. Okay, let's do this matrix multiplication. In this case, we're not multiplying by a column matrix. Okay, we're multiplying by a more complicated matrix. But we are still going to do the same thing. The only difference is instead of having a single column result from this multiplication, we're going to end up with a 2 by 2 matrix. So what we need to do is we need to match each row with each column, like we did here, matching each row with this column, and that resulting in each of these results. We're going to do the same process. It's harder with this matrix to keep an eye on what's going on, so I'm actually going to show a little trick that helps us make sure we don't make any mistakes with this matrix multiplication. So instead of setting them out like this, I'm going to set my two matrices out like this. And I might just give myself a little bit more space here. I'll make sure I get the matrices the same. Now, the advantage of setting it out like this is it helps me keep track of what I'm multiplying together at each stage. So my result is going to live in this space here. And each of these values is going to be made up by combining this row with that column. Okay, and I'm actually going to do my working over here on the side to help me out. So this first cell, I need to do 1 times 0 plus 2 times 1 plus 3 times 2. And if I work that out, oh, I keep jumping all over the place. This is 0, that's 2, that's 6. So I end up with 0 plus 2 plus 6, which is 8. So this first cell result is going to be 8. The next one, this row with this column. 1 times minus 2 plus 2 times 3 plus 3 times 4. Okay, this one's a little bit more complicated. 1 times minus 2 is minus 2. 2 times 3 is 6. 3 times 4 is 12. Minus 2 plus 6 plus 12. That's going to come out as 16. Okay, next element. 4 times 0. 5 times 1. And 6 times 2. Again, 0, this one's 5, this one's 12. 0 plus 5 plus 12 is 17. And final element of the matrix, 4 times minus 2. 5 times 3. And 6 times 4. So working that one out is a little bit more difficult. And the total of that comes to 31. So that becomes the final element in our matrix here. So this is the result of that matrix multiplication. This 2 by 2 matrix. To wrap up, I just wanted to go over some of the results that we can notice from these multiplications. So in the first matrix, in the first matrix multiplication, we had a 4 row and 3 column matrix, so a 4 by 3 matrix, and we were multiplying it by a 3 by 1 column matrix. And the result was a 4 row, 1 column matrix, or 4 by 1. Okay, might just fence this little bit off because I'm making a more general point. If we look at our second case, we had a 2 by 3 multiplied by a 3 by 2 and the result was a 2 by 2 matrix. Now have a look at this and let's see if we can notice a pattern. Notice in both these cases the number of columns in the first matrix is the same as the number of rows in the second matrix. In both cases we had 3 columns in the first matrix and 3 rows in the second matrix, and that's required because we need them to match up like this. Okay, we need to have enough elements in the row to match up with the number of elements in the column. So that always has to be the case. Okay, let's make a note of that. These must be the same. Okay, so unlike addition where we had to have the matrix orders lined up exactly, in this case we only need these two numbers to match up. Okay, something else to notice, the number of rows in the first matrix and the number of columns in the second matrix are the same as the result. So this is a 4 rows in the first column and 1 column in the second matrix. I got a 4 by 1 matrix as the result. In the second example, 2 and 2, I get a 2 by 2 matrix. So by setting them out like this, you can actually work out, first of all, whether you can do the matrix multiplication if these two numbers match up, and secondly, whether or not you can work out what the size of the resulting matrix needs to be.